Hello there. I'm glad you're here, sharing this quiet stretch of night beyond the familiar stars, far past the gentle order of our own sky. The universe holds worlds that feel almost like whispered secrets, planets where rain falls as glass, where winds carry iron, where pressure turns carbon into glittering stone. They sound like dreams or myths told too late at night, but they are real. Patiently circling distant stars, tonight we'll wander softly through these very strange planets that astronomers have discovered, learning how they form, what they're made of, and how nature, given time and distance, becomes wonderfully extreme. There's no rush, just curiosity, unfolding slowly. And if these quiet explorations bring you comfort or wonder, a gentle like and a soft subscribe help others find this calm too. For now, let the night stretch on as we begin our journey together, unhurried and calm, far from the steady rhythm of our own sky. There exists a planet locked in an endless imbalance, held so tightly by its star that it has forgotten what change feels like. 55 Cancri E moves so close to its sun that one entire side of the world is kept forever facing the light. There, the ground does not rest. Rock itself has surrendered, softened into a vast, glowing ocean of molten lava that rolls slowly under a white, punishing glare. There is no sunrise, no sunset, no relief, only heat pressing downward, unbroken and absolute. On the opposite side, the planet turns its back on the star entirely. Darkness settles there without interruption. Ancient and complete, no warmth arrives, no light wanders in by accident. The surface cools into a silent night that never ends, as though time itself has slowed and thickened. Between these two extremes lies a narrow boundary, a thin band where light weakens and heat loosens its grip. This twilight region is neither burning nor frozen, only dim and uncertain. A strip of perpetual dusk stretched around the planet like a quiet scar. It is the closest thing this world has to balance. Though even here, the ground never truly rests. Drifting onward, another planet appears. At first glance, almost gentle, HD 189-377, B circles its star alone, its surface wrapped in swirling patterns of blue and white that seem calm from afar. The colors curl and blend like paint stirred slowly in water, giving the impression of clouds, perhaps even storms familiar in spirit to those of Earth. But this beauty is deceptive. The hues are not formed by water or soft vapor. They come from hard silicate particles suspended in the atmosphere, the same materials that form rock and glass. Here, the sky does not rain water, it rains glass. Tiny shards fall endlessly, driven sideways by winds of astonishing power. These winds race around the planet at speeds reaching 5,400 miles per hour, a velocity nearing Mach 7, far beyond anything ever experienced on Earth. For comparison, the strongest wind ever measured on our world reached only 254 miles per hour, more than 20 times slower on this distant planet. The glass does not fall gently downward. It is flung across the surface at hypersonic speed, slicing through the air, scouring the landscape without pause. Nothing could stand upright for long beneath such a sky. Everything is worn down, stripped away, reduced. Not all destruction comes from storms and heat. In another system, whose name twists too sharply for the tongue, 3 exoplanets circle a star that should no longer exist as one. This star is a pulsar, the exposed, rapidly spinning core of a once massive sun that exploded long ago. Though small, it is unimaginably dense and spins several thousand times per second, sweeping beams of electromagnetic radiation across space like invisible blades. The planets that orbit this remnant are caught in those beams again and again. Each pulse strikes them with quiet violence, peeling away layers atom by atom. There is no single catastrophic moment. Instead, the destruction is slow and patient. The star eats its planets not with fire, but with time, over ages too long to feel but short by cosmic standards. These worlds are being erased. One day, there will be nothing left of them at all. No surface, no core, no memory written into orbit. Some planets endure even more intimate encounters with their stars. Kepler 70 is a hot blue dwarf star that expanded into a red giant roughly 18 million years ago. Before that transformation, it hosted at least 2 planets. The closer one, known as Kepler 70b, was once a gas giant similar in nature to Jupiter. When the star swelled outward, it engulfed the planet completely. For a time, Kepler 70b existed inside the body of its own sun. Against all expectation, it survived. But survival came at a cost. The intense heat stripped away its thick gaseous layers, leaving behind a dense, rocky core. What remains today is a planet transformed, no longer a gas giant, but a blazing, exposed world, heated to temperatures higher than the surface of our own sun. It glows with residual fury, a remnant shaped by immersion in stellar fire. Yet even now, it continues to fade. The heat is too great, the grip of the star too strong. Material escapes into space, thinning the planet slowly. Its existence is temporary, its future already written into the physics that keeps it burning. Other worlds suffer a quieter, Zeta, Fatu. WASP 12b orbits so close to its star that gravity itself becomes a weapon. The planet is composed mostly of gas, swollen and vulnerable. While its star pulls relentlessly, the result is not an explosion, but a stretching. The planet is drawn out of shape, elongated into a form that resembles an egg pulled toward a waiting mouth. Streams of gas flow away from WASP 12b, feeding the star that raised it. The planet cannot resist. It has no solid surface to anchor itself, no strength to pull back. Over time measured in millions of years, it is being devoured. In roughly 10 million years, this slow consumption will be complete. The planet will be gone, absorbed entirely, leaving behind only a slightly brighter star and an empty path where a world once circled. Heat alone does not define danger. Sometimes, cold sharpens it. Gliese 436b is a Neptune-sized planet that orbits close enough to its star to experience intense heat. Yet its surface is not molten or gaseous. Instead, it is covered in ice, burning ice. The temperatures here are hotter than a blazing oven, yet the ice remains solid. This is not ordinary frozen water under the planet's immense gravity. Water is compressed into a dense, crystalline form that does not melt easily. Even under extreme heat, walking across such a surface would be like stepping on hot coals and ice at the same time. The ground would burn and resist, solid and unyielding, shimmering under relentless radiation. The planet holds this contradiction without effort, its gravity forcing matter into states that feel unnatural only because they are so far removed from everyday experience. No gathering of extreme worlds feels complete without turning briefly toward a familiar face made hostile by circumstance. Venus, often called Earth's twin, sits second from the Sun, wrapped in an atmosphere so thick that light itself struggles to pass through. Clouds pile high, not of water, but of sulfuric acid. They condense and fall as corrosive rain, though much of it evaporates before reaching the ground. Consumed by the heat below, Venus's surface is hotter than that of Mercury. Despite Mercury being closer to the Sun, volcanic activity reshapes the landscape again and again, releasing gases that feed the suffocating atmosphere. Winds howl through the upper clouds with the strength of the most powerful hurricanes known on Earth, circling the planet endlessly. The pressure at the surface is crushing, the heat relentless, the air unbreathable. It is a world that shows how small differences in distance and composition can lead to vastly different outcomes. At the far end of this quiet journey lies a planet defined not by fire, but by cold so deep it feels absolute. Its name is long and complex, matching the harshness of the place itself, though its host star is not especially distant. The star is a small, cool red dwarf. Its light arrives weak and thin, offering little warmth. Temperatures on the planet fall as low as -370 degrees Fahrenheit, only slightly warmer than absolute zero. Here, darkness dominates. The surface is locked beneath layers of eternal ice that never thaw. No liquid flows. No softening comes with time. The world remains frozen, still, and heavy with silence. Yet even here, the story does not fully close. If the planet possesses a rocky core, slow radioactive processes deep within might generate a faint internal warmth far below the frozen shell. Hidden and unreachable, there exists a quiet possibility that something unfamiliar could persist, sheltered from the cold above. Waiting without light beneath the ice, Dimidium rests far beyond our familiar night, roughly 50 light years from the quiet warmth of our own solar system. From a distance, it might seem like just another point of mass circling a star. But nothing about this world allows for comfort. It is locked tightly to its sun, held in a gravitational grip so firm that one side is always facing the star, while the other is forever turned away. There is no rotation to soften the contrast, no slow sharing of warmth. The planet lives split in two. On the day side, heat dominates everything. Temperatures climb beyond 1,800 degrees Fahrenheit, enough to strip strength from matter itself. The atmosphere never settles. Winds sweep endlessly across the glowing hemisphere at speeds reaching 600 miles per hour, carrying heat sideways in an unbroken flow. Even the idea of seasons loses meaning here. If this is winter, it is a winter defined only by fire. Despite being a gas giant, Dimidium carries an unexpected burden. Iron, usually locked deep inside planetary cores, rises into its atmosphere. There, it melts, evaporates, and gathers into clouds that drift through the scorching air. As these clouds cool slightly, the iron condenses and falls back toward the planet below, not as solid metal, but as molten rain. Streams of liquid iron descend through the sky, glowing as they fall, testing everything beneath them. Gravity pulls it down. Heat keeps it fluid, and the cycle repeats without end. Elsewhere, oxygen makes an appearance where it offers no comfort at all. Osiris circles its star at a distance so close it feels almost reckless, 8 times closer than Mercury is to the Sun. Scientists were startled to detect oxygen around this planet, not because it hinted at life, but because here, oxygen only feeds destruction. At such proximity, the star's heat turns the planet into a living furnace. Anything that can burn does burn. Quickly and completely, Osiris moves so fast along its orbit that a full year passes in just 3.5 days as measured on Earth. The planet barely has time to cool before it is scorched again. Its atmosphere cannot hold on to itself. Heat and stellar winds strip it away continuously, pulling gases into space and thinning the envelope that once surrounded the world. Nothing lingers. Everything drifts outward, leaving the planet exposed to the star's relentless influence. Some planets do not rely on heat to inspire fear. Coroti 3b carries its danger quietly, hidden in its weight. At first, it resembles Jupiter in size, a familiar silhouette among gas giants. But beneath that resemblance lies an extreme difference. This planet is 20 times denser than Jupiter. Its mass compressed into a smaller, heavier form. Gravity there is overwhelming, about 50 times stronger than what is felt on Earth. On such a world, standing would not be possible. The atmosphere itself presses downward with crushing force. Any structure, any body, any attempt at balance would fail instantly. The planet does not need fire or storms to be hostile. Its density alone is enough. Everything is pulled inward, held tight, leaving no room for movement or escape. Another world, Kepler 7b, returns to heat, but heat taken to an almost unimaginable extreme. Day after day, temperatures rise above 4,000 degrees Fahrenheit. The surface is rocky, yet rock behaves differently here. Stones bubble and boil as if they were liquid, slowly evaporating into the atmosphere. Once lifted, these vapors cool just enough to condense, falling back down as a rain of brimstone. The ground is constantly reshaped, not by water or wind, but by its own substance cycling through air and surface. There is a quiet sadness woven into Kepler 7b's story. Astronomers suspect it may once have been a gas giant, rich and expansive, before drifting too close to its star. Over time, heat stripped its atmosphere away, layer by layer, until only the scorched core remained. What survives today is not what it once was, but a remnant, enduring under conditions that ensure nothing lasts forever. These worlds feel violent and final, yet they all share a common origin story, one that begins gently, almost invisibly, around young stars still forming in their earliest stages. Stars are surrounded by vast, rotating disks of gas and dust. These disks stretch outward like soft halos, glowing faintly as they circle. Most of the material slowly falls back into the star, drawn inward by gravity, but not all of it. Within the disk, dust particles drift and collide. When these collisions are gentle, the particles cling together. At first, the clumps are no larger than the width of a human hair. Time passes millions of years unfolding quietly, and the clumps grow. Dust becomes pebbles. Pebbles merge into larger rocks. Gas in the disk acts like a cushion, slowing movement and helping these fragments stay together. Some break apart again, undone by violent impacts, but many survive. Eventually, these growing bodies become planetesimals, the building blocks of future planets. As they orbit, they clear paths through the disk, sweeping up material or flinging it away. What remains behind them is mostly fine dust, drifting lazily where chaos once ruled. The disk itself begins to change. As it thins and cools, it stretches farther from the star's heat. Far from the star, temperatures drop low enough for water to freeze. Ice joins the dust, and tiny frozen particles swirl through the outer regions. Over time, they gather into snowball-like forms that grow steadily larger. These icy cores become massive enough to pull gas toward them. In the cold, gas molecules move more slowly, making them easier to capture. Layer by layer, giant planets begin to form, wrapped in thick atmospheres of hydrogen and helium. Astronomers believe this is how gas giants like Jupiter, Saturn, Uranus, and Neptune came into being. Jupiter and Saturn formed first, assembling their enormous masses in roughly 10 million years, a brief moment by cosmic standards. Closer to the star, conditions were harsher. Gas was driven away more easily, leaving behind heavier materials. There, rocky planets began to take shape. These inner worlds formed more slowly. Tens of millions of years passed as rock collided with rock. Heat built up, and surfaces hardened. Once planets settled into stable paths around their star, a planetary system emerged, a family of worlds sharing a common origin. Such systems may include moons, asteroids, dwarf planets, meteoroids, and comets, all bound by gravity and time. Our own system is one such arrangement. The Sun and the 8 planets that circle it form what we call the solar system. Closest to the Sun is Mercury, a small world that from a distance looks eerily like Earth's moon. Its surface is scarred with craters, shaped by countless impacts. Up close, the resemblance fades. Mercury is a planet in its own right, one of the 4 rocky worlds orbiting our star. Mercury is the smallest of these inner planets, measuring about 3,000 miles across at its equator. To circle the planet entirely would take roughly 2.5 days if one could drive without stopping at a speed of 50 miles per hour. Yet traveling there would be anything but smooth. The surface rises and falls sharply, littered with massive hills and steep slopes. Some of these reach heights of 2 miles, towering over the surrounding plains. There is no true atmosphere to soften conditions. During the long days, temperatures soar to 800 degrees Fahrenheit. At night, without air to trap warmth, They plunge to minus 290 degrees Fahrenheit. The contrast is extreme. Yet Mercury holds itself together through sheer density. It is the second densest planet in the solar system, surpassed only by Earth. At its heart lies a massive metallic core, taking up nearly 85% of the planet's total volume. This core contains more iron than that of any other planet in the solar system. Astronomers now believe it may consist of both a liquid outer layer and a solid inner core, layered deep beneath the surface. Above it rests a rocky mantle and a solid crust only 300 to 400 miles thick, instead of an atmosphere. Mercury possesses a thin exosphere, a sparse collection of atoms, including oxygen, sodium, hydrogen, helium, and potassium. These particles drift loosely around the planet, never forming a stable blanket. Mercury sits too close to the sun to hold them. Solar wind sweeps past constantly, and micrometeoroids strike the surface without warning, knocking particles free and carrying them away. Nothing lingers for long. The planet stands exposed, slowly and endlessly scoured by light, wind, and stone. Venus comes into view looking nothing like the soft, bluish world so often captured in distant images. From close range, its colors shift and darken. The surface below is not pale or gentle, but reddish-brown, dry, and harsh, shaped by heat and pressure that never loosen their hold. The planet is wrapped in an atmosphere so dense it feels less like air and more like a crushing ocean made of gas. Carbon dioxide dominates almost everything here, building a blanket so thick that light struggles to move through it. Above the surface, enormous clouds drift by clouds, not of water, but of sulfuric acid. They swirl slowly, layer upon layer, reflecting light while hiding what lies below. These clouds condense and fall as corrosive rain, though much of it never reaches the ground. The heat consumes it on the way down, returning it to vapor. Venus is thirsty in the most ironic way. Water, the simple molecule known as H2O, is rare and precious here. Other compounds that resemble it only bring destruction. Nothing about this sky offers relief. The ground beneath those clouds tells its own story. Vast, smooth plains stretch across nearly 2/3 of the planet, flattened by ancient lava flows that spread and cooled long ago. These plains are interrupted by mountains, most of them volcanoes. Many appear dormant now, but some may still be active, quietly reshaping the surface. Two enormous highland regions rise above the plains, one comparable in size to South America, the other to Australia. Between them lie broad lowlands and long, winding channels carved by rivers of lava. Some of these hardened flows extend for 3,000 miles, frozen traces of a more violent past. Heat is trapped relentlessly by the thick atmosphere. Like Earth, Venus experiences a greenhouse effect. But here, it has grown unchecked. Temperatures climb to 880 degrees Fahrenheit, hot enough to melt lead. The pressure at the surface is overwhelming, about 90 times greater than the pressure felt at sea level on Earth. It is comparable to standing beneath 3,000 feet of ocean water. Everything is pressed downward. Nothing is allowed to expand or breathe. Deep inside Venus, the planet is layered and heavy. At its center lies a metallic iron core, roughly 2,400 miles wide, nearly the distance from New York to Los Angeles. Surrounding it is a molten, rocky mantle, about 1,200 miles thick, slowly shifting and carrying heat outward. Above that rests a crust made mostly of basalt, between 6 and 12 miles thick. It is thin, brittle, and cracked by time. The atmosphere above all of this is nightmarish in composition, about 96% carbon dioxide, 3% nitrogen, and thick clouds of sulfuric acid. Venus is sealed in on itself, holding heat until moderation is no longer possible. Not far away, another rocky world takes a very different path. Earth, the third planet from the Sun, appears from space like a blue marble, streaked with green, yellow, brown, and white. The blue dominates. Water covers 71% of the surface, shaping coastlines, carving valleys, and reflecting light back into space. Even from orbit, familiar features stand out. The Great Barrier Reef traces a pale line near Australia, stretching for 1,600 miles. The Grand Canyon cuts across North America, its 277 miles visible in a single glance. Earth is the densest planet in the solar system. Beneath its surface lies a carefully balanced interior. At the center is a core that takes up about 15% of the planet's total volume. This core is divided into two parts. The inner core is a solid sphere made mostly of iron and nickel, with a radius of 760 miles. That is about 20% of Earth's radius, and roughly 70% of the Moon's radius. Surrounding it is the outer core, a liquid layer about 1,500 miles thick, also rich in iron and nickel. Here, pressure is not quite enough to force the metal into a solid state. At the boundary between these two cores, temperatures reach 10,800 degrees Fahrenheit, comparable to the surface of the Sun. Pressure there is 3.3 million times greater than the atmospheric pressure at sea level. Above the core lies the mantle, a thick shell roughly 1,800 miles deep. It makes up nearly 84% of Earth's total volume and consists of silicate rocks rich in iron and magnesium. The mantle moves slowly, flowing over geological time like thick paste, carrying heat upward. The crust sits atop this massive interior, thin and fragile by comparison. It accounts for only about 1% of Earth's volume. Together with the upper mantle, it is broken into tectonic plates that drift at a pace similar to the growth of human fingernails. Their movement allows heat to escape from the planet's interior and reshapes the surface continuously. The crust itself is composed largely of oxygen, silicon, aluminum, iron, and other minerals, arranged into continents and ocean floors that never truly stop changing. Farther from the Sun, the warmth fades. Mars, the fourth planet, marks the outer edge of the inner. Rocky worlds, it is often called terrestrial, like Mercury, Venus, and Earth, built from rock and metal rather than gas. But Mars feels incomplete, as though it cooled too quickly. Temperatures there can drop to -80 degrees Fahrenheit, and cold defines much of its character. From afar, Mars glows red. The color comes from iron-rich dust coating the surface, rusted and fine. That same dust floats through the thin atmosphere, tinting the sky and softening the horizon. Up close, the planet reveals subtle variation: golden brown plains, tan deserts, and even faint greenish hues, depending on the minerals present in the soil. In many regions, the dust layer is about 7 feet thick, settling gently over rock like talcum powder. The Martian surface is rugged and dry, shaped by craters, ancient lake beds, sprawling canyons, and massive volcanoes. Olympus Mons rises higher than any other mountain in the solar system. It stands 2.5 times taller than Mount Everest and spans an area roughly the size of Arizona. Its immense scale speaks to a time when the planet was more active, its interior warmer and more willing to push upward. Mars's atmosphere is thin, containing about 95% carbon dioxide and only 1% oxygen. It offers little protection. Dust storms can grow so large they engulf the entire planet, wrapping Mars in a hazy shroud visible even from Earth. These storms eventually settle, leaving the surface quiet again. Beneath the surface, Mars is simpler than Earth. Its core, made mostly of iron, nickel, and sulfur, measures between 900 and 1,200 miles across. Unlike Earth's core, it no longer moves. Without that motion, Mars lacks a global magnetic field. The mantle above it is composed of thick silicates, oxygen, and various minerals, often compared to soft, rocky toothpaste in texture. It is thinner than Earth's mantle, measuring between 800 and 1,100 miles. The crust of Mars is made primarily of volcanic basalt. Astronomers believe it is not divided into tectonic plates, but remains a single, unbroken shell. Over time, it has been blanketed by fine red dust, settling into every low place and softening every edge. The planet rests beneath that layer, quiet and still, its surface unchanged, except for the slow movement of wind and the patient fall of powder-fine grains. Beyond the cold stillness of Mars, the solar system opens into a realm where solidity begins to dissolve. Here, worlds no longer offer ground beneath one's feet. Instead, they swell outward into vast volumes of gas and liquid, layered and restless, shaped more by pressure and motion than by rock. The first of these giants is Jupiter, a presence so large that it quietly dominates everything around it. Jupiter is the largest planet in the solar system, stretching more than 89,000 miles across at its equator. Its size is difficult to hold in the mind. More than 1,300 Earths could fit inside its immense volume, leaving space to spare. Yet, despite this enormity, Jupiter does not feel slow or inert. It is active, churning, alive with motion. Deep within, the planet grows unimaginably hot. Temperatures near its center climb toward 43,000 degrees Fahrenheit, a heat generated not by a nearby sun, but by gravity itself, squeezing matter inward until it glows. There is no surface to land on here. Jupiter is a gas giant, composed mostly of hydrogen and helium. From afar, it appears wrapped in bands of color brown, yellow, to red, and white clouds stretching horizontally around the planet. These stripes are not painted on a solid shell. They are layers of atmosphere moving at different speeds, sliding past one another endlessly. The colors shift subtly over time, shaped by chemistry, temperature, and light. Among these bands lies one of the most enduring storms ever observed, the Great Red Spot. This enormous vortex has been spinning for at least 360 years. It is a storm so large that Earth itself could fit comfortably within its swirling boundaries. Its color changes slowly, ranging from pale salmon to deep brick red, as if the planet is breathing pigment in and out. Winds race around this storm at tremendous speeds, joining the broader atmospheric currents that sweep across Jupiter at anywhere from 200 to 400 miles per hour. Jupiter's mass is so great that, had it been roughly 80 times heavier, it might have crossed the threshold into becoming a small red dwarf star. It sits just below that line, forever a planet, never igniting nuclear fusion at its core. Even so, what lies at Jupiter's center remains uncertain. Some evidence suggests a core between 14 and 18 times the mass of Earth. Possibly rocky, possibly molten, perhaps even dissolving into the surrounding layers. There are hints that this core may be melting right now, slowly blending into the dense material around it. As pressure increases deeper within the planet, hydrogen and helium no longer behave as gases. They compress into a dense fluid, and closer still to the core, hydrogen transforms into a metallic state, capable of conducting electricity. This metallic hydrogen may play a role in generating Jupiter's powerful magnetic field, though many details remain hidden beneath thousands of miles of atmosphere without solid ground. Astronomers define Jupiter's surface as the level where atmospheric pressure matches that of Earth's sea level. Even there, one could not stand. Gravity at that height is more than 2.5 times stronger than on Earth, pulling everything inward without mercy. Farther out, another giant waits, similar in nature, yet gentler in presence. Saturn shares Jupiter's basic composition, mostly hydrogen and helium, but it feels lighter, softer, almost delicate by comparison. Like Jupiter, Saturn has no solid surface. If one could descend into its atmosphere, temperature and density would change gradually with depth. There would be no clear boundary, no sudden moment of arrival. One would simply keep falling. At the upper layers, Saturn's gravity feels surprisingly familiar, close to that of Earth, but the density there is low, offering no resistance. A fall would begin slowly, then accelerate as pressure increased. Deeper down, the atmosphere would thicken until movement became impossible, and eventually the pressure would grow strong enough to crush anything solid from above. Saturn appears to have a surface, a smooth, yellowish-brown sphere, but this is only an illusion created by cloud layers. The visible outer clouds are made mostly of ammonia. Beneath them lie clouds of ammonium hydrosulfide, and deeper still, clouds of water. Winds on Saturn are fierce, especially near the equator, where they can reach speeds of 1,100 miles per hour. For comparison, the strongest winds on Earth rarely exceed 250 miles per hour. These currents race around the planet, shaping the atmosphere into bands and waves that shift slowly over time. Saturn's composition is similar to Jupiter's, though it contains more sulfur, lending the planet a soft, smog-like orange hue. As with Jupiter, pressure increases steadily with depth. Hydrogen eventually liquefies, and closer to the center, it transitions into metallic hydrogen. Saturn, too, may possess a core made of rocky material, surrounded by hydrogen and helium. Even if this core is rocky, it may not be solid. Under such conditions, rock itself can behave like liquid, flowing slowly rather than holding shape. One of Saturn's most recognizable features floats far above these hidden depths. Its rings form a broad, luminous system encircling the planet, composed of countless chunks of ice and rock. These pieces range in size from tiny grains to large fragments, all orbiting in delicate balance. The rings appear gray, beige, and tan, catching sunlight and scattering it softly into space. They are not a single structure, but many narrow ringlets grouped together, each following its own path. Saturn is accompanied by a large family of moons. 53 have been confirmed and named, with another 29 still awaiting confirmation and official designation. Among them, Titan stands out. This icy world is larger than Earth's moon and even bigger than Mercury. It circles Saturn quietly, a massive companion wrapped in its own mysteries. Though it remains firmly part of Saturn's domain, despite its size, Saturn is the least dense planet in the solar system. Its average density is about 1/8 that of Earth. In a thought experiment often repeated, if a body of water large enough existed, Saturn would float upon it. Yet this lightness is deceptive. Because of its enormous volume, Saturn is still 95 times more massive than Earth. Size and density tell different stories here, woven together into a world that defies simple intuition. Even farther from the Sun, where light weakens and time stretches, a different kind of giant drifts through space. Uranus lies about 1.7 billion miles from the Sun, appearing as a calm blue-green sphere against the dark. Its color comes from the way sunlight reflects off its atmosphere, filtered through methane that absorbs red wavelengths and leaves behind cool tones. Uranus is often called an ice giant, though it is not frozen solid. Like Jupiter and Saturn, it lacks a solid surface. If a small asteroid were to collide with Uranus, it would pass through the upper atmosphere and sink into the planet's icy, liquid interior. Beneath the clouds lies a dense mixture of water, ammonia, and methane, forming a slushy, super-pressurized mantle surrounding a rocky core. One of Uranus's most striking features is its orientation. The planet orbits the Sun on its side, with its axis tilted almost directly toward the star. This unusual position may be the result of a massive collision early in its history, a violent encounter that knocked the planet over and left it rolling through space at an extreme angle. Because of this tilt, Uranus experiences seasons unlike any other planet. For long stretches, one hemisphere faces the Sun continuously, while the other remains in darkness. During periods when Uranus receives more sunlight, powerful storms can erupt. These hurricanes are rare and extreme, appearing only when the planet is heated enough to drive strong atmospheric motion. Some of these storms can stretch for more than 6,000 miles, nearly the distance between Japan and the United States. They move slowly across the planet's face, then fade as temperatures drop again. Uranus also possesses rings, though they are less famous than Saturn's. Two distinct ring systems circle the planet. The inner system consists of 9 narrow, dark rings, subtle and difficult to see. Farther out lie brighter rings, one tinted blue, another red, adding quiet structure to the planet's surroundings. They drift silently, held in place by gravity and motion, completing the picture of a world that is both serene and deeply strange. Turning gently on its side in the cold outer reaches of the solar system, deep beneath the calm blue-green skin of Uranus. The planet grows quieter rather than more violent. At its very center rests a rocky core, surprisingly small when compared to the planet's vast size. Its mass is only about half that of Earth, and by planetary standards, it is not especially hot. Temperatures there rise to roughly 9,000 degrees Fahrenheit, a gentle warmth compared with the blazing hearts of Jupiter or Saturn. Uranus carries its energy differently, storing less heat, releasing it more slowly, as if the planet itself prefers stillness. Surrounding this modest core is a thick mantle that dominates the planet's interior. It accounts for nearly 80% of Uranus's total volume and is often described using the word ice. Though the term is misleading, this is not ice as it exists on Earth, brittle and cold. Instead, it is a hot, dense fluid made of water, ammonia, and methane, crushed together under immense pressure. Some scientists describe it as a water-ammonia ocean. Though it behaves nothing like the seas we know, it does not ripple or reflect light. It flows slowly, heavily, carrying heat in silence. Above this deep mantle lies Uranus's atmosphere, composed mostly of hydrogen and helium. Methane drifts through it in smaller amounts, yet its effect is unmistakable. Methane absorbs red wavelengths of sunlight, allowing blue and green tones to scatter back into space. That is why Uranus appears so softly colored, like a pale jewel set against darkness. The planet does not shout its presence. It rests there quietly, tilted on its side, conserving its internal warmth. Farther still from the sun, another world circles in colder light. Neptune is more compact than Uranus, only about 4 times the size of Earth. Yet it is far heavier, roughly 17 times Earth's mass. What looks like a smooth blue surface in images is not a surface at all, but a restless layer of swirling gas and permanent clouds. Beneath those clouds lies Neptune's mantle, made of water, ammonia, and methane in a dense, heated mixture. This region is the closest thing Neptune has to a surface, though it offers nothing solid to stand upon. Traveling inward through Neptune would mean crossing extreme contrasts. Near the outer layers, temperatures can fall to around -340 degrees Fahrenheit. Deeper down, heat rises sharply, climbing to more than 12,000 degrees Fahrenheit near the core. These dramatic temperature differences drive powerful storms. Winds accelerate as energy moves upward, reaching speeds of about 1,200 miles per hour. It is this constant motion that earns Neptune its reputation as the windiest planet in the solar system. The planet does not merely endure its energy, it releases it through movement. Like Uranus, Neptune is classified as an ice giant. At its center lies a solid core composed mostly of iron and other heavy elements. This core has a mass about 1.2 times greater than Earth's. Surrounding it is a vast mantle, a superheated liquid layer where temperatures range between 3,000 and 8,500 degrees Fahrenheit. This mantle alone contains material equal to as much as 15 Earth masses. It is rich in methane, ammonia, and water, compressed into unfamiliar states by pressure. Within these depths, something remarkable may occur. At a distance of roughly 6,200 miles below Neptune's cloud tops, conditions may allow carbon atoms to rearrange themselves into diamond crystals. These crystals would form slowly, falling like rain through the dense mantle, sinking toward warmer regions where they might dissolve again. It is a quiet process, hidden far below the clouds, driven not by spectacle, but by physics. Neptune's atmosphere forms only about 5 to 10% of the planet's total mass. Yet it stretches deep about 20% of the way toward the core. It consists of roughly 80% hydrogen, 19% helium, and a small amount of methane. As with Uranus, methane shapes the planet's color, filtering sunlight until Neptune appears a deeper blue. The planet glows softly, restless and distant, shaped by forces that never pause. After tracing the outer edge of our own planetary neighborhood, a natural curiosity begins to drift outward, beyond the sun's reach, beyond familiar orbits. Other stars hold their own collections of worlds. Planets that do not belong to our solar system are known as exoplanets, worlds circling distant suns, shaped by the same physical laws, yet often arriving at very different outcomes. Roughly 40 light-years from Earth, near a small red dwarf star, lies an exoplanet called GJ 1214b. This world is about 3 times the size of Earth, yet its mass is 8 times greater. It orbits its star once every 38 Earth hours, remaining close enough to receive constant heat. Surface temperatures reach around 400 degrees Fahrenheit, warm enough to keep water from behaving normally. Observations made using the Hubble Space Telescope suggest that this planet is unlike anything found in our own system. GJ 1214b appears to be a giant water world, enveloped by a thick, steamy atmosphere. Beneath that atmosphere, water may exist in exotic forms. High pressure and heat could transform it into superfluid states or hot ice phases where water remains solid despite intense temperatures. There is no shoreline here, no familiar ocean. Instead, water becomes something heavy and strange, molded by conditions far beyond everyday experience. Another distant planet, located about 62 light-years from Earth, appears at first glance almost peaceful. Its blue coloration can feel familiar, echoing the look of Earth from space. Yet this resemblance is only surface deep. The planet is slightly larger than Jupiter, and its color comes not from water, but from silicate particles suspended in its atmosphere. These particles scatter light, creating a soft blue hue that hides a far harsher reality. Winds on this world reach speeds of roughly 5,400 miles per hour, about 7 times the speed of sound. Temperatures rise above 1,600 degrees Fahrenheit. Under these conditions, silicate particles do not remain suspended gently. They condense into sharp fragments and fall as rain, not downward, but sideways. Driven by the relentless winds, it rains glass here, horizontally, endlessly. A storm like this on Earth would circle the planet in about 5 hours, scouring everything in its path before fading. On this distant world, such storms never truly stop. In another strange system, astronomers discovered a planet roughly the size of Neptune, orbiting a star no larger than Earth itself. This pairing seems backward, as stars are usually far more massive than the planets around them. The explanation lies in the nature of the star. It is no longer a typical star, but a white dwarf, a stellar remnant. The dense core left behind after a star has exhausted its fuel. This white dwarf is a stellar skeleton, unable to fuse elements in its core, yet still intensely hot. Its temperature reaches about 49,500 degrees Fahrenheit. That heat radiates outward, slowly vaporizing the nearby planet. Streams of material are pulled away at a staggering rate, around 260 million tons every day. The planet is losing its atmosphere grain by grain, carried off into space by the lingering heat of a star that has already died. Even farther away, about 30 light-years from Earth in the constellation Leo, another paradoxical world circles a red dwarf star. Gliese 436b is roughly the size of Neptune and completes one full orbit in just 2 Earth days. It travels extraordinarily close to its star, at a distance about 15 times smaller than the gap between Mercury and the Sun. Because of this proximity, surface temperatures rarely fall below 800 degrees Fahrenheit. And yet, despite this heat, the planet contains enormous amounts of water ice. Not ordinary ice, but a dense crystalline form known as Ice 10. This ice does not melt under the planet's immense gravity. Even trace amounts of water vapor are compressed until they freeze into this exotic state. The pressure holds the ice together, preventing it from turning into liquid despite the surrounding heat. On Gliese 436b, gravity decides the rules, pressing matter into forms that defy intuition, leaving water locked in solid silence beneath a burning sky, far beyond the familiar patterns of our sky. There exists a world so dense and compact that it challenges the way matter itself is usually imagined. Roughly 4,000 light-years from Earth, a planet circles a star that is no longer truly a star. Its parent is a pulsar, the exposed core of a once massive sun that ended its life in a violent explosion and now spins with astonishing speed, rotating about 10,000 times every single minute. Around this restless remnant, the planet completes an entire orbit in just 2 hours and 10 minutes. Time compressed into a relentless loop. This planet is about 5 times the size of Earth, yet far heavier than its appearance suggests. It is denser than any other planet discovered so far. Its composition is dominated by carbon, squeezed so tightly by gravity that astronomers believe much of that carbon may have crystallized. Under such pressure, carbon does not remain soft or granular. It locks into rigid structures deep within this world, and perhaps across large portions of it. Carbon may exist as diamond, not scattered gems, but vast regions of crystalline material formed quietly by physics. There is no sparkle here, no reflection meant for eyes. The diamond is simply the stable form matter chooses under conditions this extreme. Other worlds trade pressure for heat. Some planets orbit their stars so closely that their entire existence is shaped by proximity. These are often called hot Jupiters, gas giants forced into orbits uncomfortably near their suns. WASP 7, 6b is one such planet, drifting about 640 light-years away from Earth. It is only slightly smaller than Jupiter. Yet its environment is far more severe. This planet is locked to its star by gravity. Unable to turn freely, one side faces the star at all times, bathed in relentless radiation. On this day's side, temperatures rise to around 4,300 degrees Fahrenheit, hot enough to vaporize metals. Iron does not remain solid. It lifts into the atmosphere as gas. Winds carry it away from the blazing hemisphere toward the night side, where temperatures drop just enough for the metal vapor to condense. There, iron falls from the sky as rain. It is a slow, heavy precipitation, driven by gravity and cooled darkness. On this world, metal cycles between sky and depth, day and night, repeating endlessly. The reason for such extremes lies in distance. WASP 76b orbits roughly 10 times closer to its star than Mercury does to the Sun. This closeness binds both star and planet in a tight gravitational embrace, locking one face into perpetual day and the other into eternal night. Between these hemispheres, winds race to redistribute heat, shaping weather unlike anything known closer to home. Not all strange planets belong to stars at all. Closer to Earth, only about 20 light-years away, a massive world drifts through the Milky Way without a sun of its own. This is a rogue planet, roaming the galaxy alone. It does not shine by reflected starlight, yet it is far from invisible. This planet possesses an extraordinarily powerful magnetic field, about 4 million times stronger than Earth's. Such strength bends charged particles with ease, sculpting space around it. When this object was first observed in 2016, astronomers believed they had found a brown dwarf, an object too large to be a planet and too small to ignite as a star. Later studies revealed that it was small enough to be considered a planet after all. Though it remains enormous by planetary standards, its radius is about 1.2 times that of Jupiter, and its mass exceeds Jupiter's by more than 12 times. This immense magnetic field gives rise to spectacular auroras, unlike the auroras on Earth, which are driven by interactions between the solar wind and our planet's magnetic field. These lights may be powered by a different process. Scientists suggest that a moon orbiting this rogue planet could be feeding charged particles into the magnetic environment, triggering glowing displays that ripple across the planet's atmosphere. Even without a star, motion and interaction create light. Some planets are defined not by isolation, but by excess. J1407b is often described as a super Saturn, or Saturn pushed beyond familiar limits, located about 434 light-years from Earth. This exoplanet is surrounded by an enormous system of rings. These rings are not merely larger than Saturn's, they are about 640 times more extensive. They stretch outward in a vast, delicate disk made of countless fragments. If this planet were somehow placed where Saturn orbits in our solar system, its rings would dominate the sky. From a nearby vantage point, they would appear many times larger than the full moon does from Earth. Arching overhead in layered bands, astronomers have noticed a distinct gap within these rings. Roughly halfway through their span, this empty region suggests the presence of a moon, perhaps as large as Mars, carving a path through the debris as it orbits. The rings remain balanced, shaped by gravity and motion, their scale almost difficult to comprehend. Closer still, about 20 light-years away in the constellation Libra. Another exoplanet follows a very different pattern. Gliese 581c orbits its star at an extremely close distance, only about 7% of the 93 million miles that separate Earth from the Sun. This proximity locks the planet in place. One hemisphere always faces the star, absorbing heat without pause. The other remains in permanent darkness. On the sunlit side, temperatures climb to extreme levels. On the dark side, cold dominates. Between these regions lies a narrow band, a twilight zone, where conditions are more moderate. This thin strip receives angled light and partial warmth, avoiding both burning heat and deep freeze. Scientists note that such zones could, in principle, allow more stable conditions, yet nothing is promised here. The balance is fragile, and the environment remains harsh by familiar standards. Some planets push the boundaries of imagination even further through their chemistry. HAT P7b lies more than 1,000 light-years from Earth. On its night side, the atmosphere contains significant amounts of aluminum oxide, also known as corundum. Corundum is the mineral form of sapphires and rubies. Under the right conditions, storms on this planet may cause these compounds to condense and fall. Rain here would not be water or metal, but gemstones, sapphires, and rubies carried by violent winds and scattered across the surface below. Another world hides its strangeness not in brightness, but in darkness. WASP 12b is one of the darkest exoplanets ever observed. Its atmosphere absorbs more than 94% of the light that strikes it, reflecting almost nothing back into space. The planet appears dim not because it lacks energy, but because it consumes light so efficiently. This gas giant is roughly twice the size of Jupiter and orbits extremely close to its star, completing a full circuit in less than one Earth day. On its day side, temperatures reach around 4,000 degrees Fahrenheit. The night side is cooler, yet still blistering, at roughly 2,200 degrees Fahrenheit. This temperature difference drives constant motion. Water vapor and clouds form on the cooler side, then are torn apart by winds and dragged back toward the heat. Streams of superheated gas spill away from the planet, pulled toward the star by gravity, slowly thinning the atmosphere over time. Some worlds reveal their youth through color. Gliese 504b, located in the constellation Virgo, stands out with a striking magenta hue. It orbits its star at a distance about 9 times greater than the distance between Jupiter and the Sun. This planet is relatively young, still retaining much of the heat from its formation. That internal warmth causes it to glow faintly, giving it a pinkish appearance unlike anything seen among older, cooler planets. Farther still, about 20,000 light-years away, in the constellation Sagittarius, a cold red dwarf star hosts a planet defined by distance and ice. This world orbits so far from its parent star that it receives very little heat. Surface temperatures fall below -360 degrees Fahrenheit. Under such conditions, the entire planet is encased in thick ice. Glaciers stretch across vast plains. Canyons and mountains rise, all sculpted from frozen material. Nothing melts at the surface. Nothing flows. And yet, even here, the story does not fully end in stillness. Astronomers believe that deep beneath this frozen shell, the planet's core may still generate heat. Radioactive processes and residual warmth could slowly melt ice from below. If that heat is sufficient, an enormous subsurface ocean could exist. Hidden far beneath layers of solid ice, it would be dark, sealed away from the surface, warmed only by the planet's interior liquid water, protected by pressure and time, moving quietly beneath a world that appears, from above, completely frozen.